So hypothesis testing is simply a statistical method that we use to test differences that exist between two sample means or more. So under hypothesis testing, we have key terms or keywords such as the null hypothesis, which is denoted by HO, and the alternative hypothesis, which is denoted by HA. We also have the p-value. We also have the test statistic, which is the Z calculated or the T calculated, which we are calculating, and also the process of testing the hypothesis. So these are the key terms that we're going to use. And to start with, under hypothesis testing, we're going to look at what is denoted as the null hypothesis, which is simply the hypothesis to be tested. The assumption. A hypothesis is simply an assumption, a theory, or a claim that has to be tested. So if we're claiming to say it is believed that a 20 kg bag should weigh 20 kg, that's a claim. So the belief to be tested always comes in what we call the null hypothesis. And the alternative hypothesis is simply a statement of what we believe is true if our sample data this is a statement of what we believe is true if our sample data cause us to reject the null hypothesis. So whenever we reject the null hypothesis, then this is what we may believe to be true whenever we reject the null hypothesis. In short, it is the opposite of what we have in what we call the null hypothesis. So we always have two, the null hypothesis and the alternative hypothesis. So we also have what we call type 1 and type 2 error. The type 1 error is one where we fail to reject the null hypothesis when it is actually supposed to be true. We call that the type 1 error. Okay? When we fail to reject the null hypothesis, which happens to be true, or which happens to be the correct action, we call that the type 1 error. When we fail to reject the null hypothesis, which happens to be the correct course of action, we call that type 2 error. So you need to understand what type 1 error and type 2 error is. Whenever we fail to reject the null hypothesis when it is a true course of action, we call that a type 1 error. Okay, so before we go in depth,
Colin, sorry, I lost you for a few seconds. Could you kindly explain type 2? Again.
sorry, what was the question? Please don't call me whilst class is on. Okay.
Well, I was saying I lost you for like a few seconds, so I didn't get what you explained on type 2.
Okay.
Type 2.
Can you hear me? Can you get me? Can
I
you get
get you
me?
now.
All right. Okay.
I couldn't get you before.
Okay. Sorry. Please don't call me whilst during class because it will affect the class. So I'm just trying to explain this table to say we have what we call type 1 and type 2 error. Type 1 error means we are rejecting the null hypothesis when it's actually true or it's actually correct. Whilst type 2 error means we're failing to reject the null hypothesis when it's actually false. So type 1 error, this is the error that is committed whenever we are rejecting the null hypothesis when it's actually true. So when you reject the null hypothesis when it's supposed to be accepted, we commit what we call a type 1 error. A type 2 error is simply us failing to reject the null hypothesis when it's actually false. Can somebody summarize what I've just said? So since we have the null hypothesis and the alternative hypothesis, there are times when we are supposed to reject the null hypothesis, then we are accepting the alternative hypothesis. So whenever we reject the null hypothesis when we are actually supposed to accept it, we commit what is actually a type 1 error. Type 2 error, we actually commit it when we are failing to reject the null hypothesis when it's actually false. Is that clear now?
It's clear.
All right. So in short, type 1 error occurs if you, who's the investigator, rejects the null hypothesis when it's in fact supposed to be the true. And the type 2 error is actually committed when you, the investigator, fails to reject the null hypothesis when it's actually a false, is false in the population. Okay, so we now go into the steps that are involved in testing hypothesis. Step 1, we need to state the hypothesis, which can be mu is equal to 0 or mu is not equal to 0 as alternative hypothesis. So this case that we are dealing with here is called a two-tailed test. For a two-tailed test, the signs that we use are equal to or not equal to. Then when we have a statement to say we want to test that the population mean is different than 50. So in this case here, we're not told whether it is greater or less than. So you can use the two-tailed test. It could be different in a lesser version or it could be different in a more version. So this is an unbiased hypothesis that you can have. So we use a two-tailed test to test our hypothesis. But whenever the statement that we want to test is to suggest that one population is more than the other, for instance, we want to test that the population is greater than 50. So our alternative hypothesis will have a greater sign. So say mu is equal to mu o, and then here mu is greater than the amount that we're talking about, which is 50. So here mu is equal to 50, or mu is greater than 50. So in the alternative hypothesis, we're going to use a greater sign, which will suggest that this is a single-tailed test. So you need to distinguish really basically how to know whether this is a single-tailed test or this is a double-tailed test. Now, to expand much on what I'm discussing here, we need to understand that there are what are called confidence levels, and there's what we call a significance level, and there's what we call our alpha, and there's what we call a Z, alpha over 2. So we have 4 common levels of significance and levels of confidence. So we have what we call the 99% confidence level. When it's subtracted from 100, the difference is 1%. So this is called a significance level. When you divide this significance level by 100, we get 0.01. This is called our alpha. Then in the table, this will give you what called the 2.58 z-score. This is for a two-tailed test, and the two-tailed test looks like this. Here and here. So this 1% is divided into two parts. So here we have 0.1%, and here also we have 0.1%. So this addition will give us the 1% significance level. So 0.5, half of 1 is 0.5. So even here is 0.5. Then what remains inside here? Okay, what remains inside here is 99%, the confidence level. So this confidence level, this 0.5 here, when it's subtracted from 100, we get 99.5. 99.5%. When you read it from inside the table, you're going to find 0.9950. Then you check this number from inside the table, it will give you the 2.58. I'll stress this much more tomorrow in the physical classes, but just not to waste much time on where these figures are coming from. For those of you who could be curious to finding them out, there's what we call our statistical table. So whenever you're looking for figures, for instance, inside the table, you will go and check under which one is coinciding to 0.995. You'll find it under 2.58. So when you go inside the table here, check it from inside here, you will discover that this one is close to 0.9950. This is 9951. So this, when you collectively add, it will give you 2.58. So this is where the 2.58 is coming from, here. So you just need to memorize our song. Remember our song which we've been singing. So if this is 98%, class, what we have here as a level of significance? 2%. Then when you divide the 2% by 100, what we have? 0.02. Then this from inside the table, you're going to find 2.33. Then we also have 95%. Then here we have 5%. The difference from 100, these two must add up to what? 100. Then this is 0.05. And this is 1.96. Then finally we have 90%. The difference from 100 is what? 10%. When we divide it by 100, it's 0.10. This will give us 1.645. So these are key figures. So this is what we call a two-tailed test, where you are going to have the signs equal to or not equal to. So meaning it looks like this. But if it's a single-tailed test, it means only one tail will be shaded. The right side denotes greater than. The left side denotes less than. So both of these are called what? Single-tailed test. So for a single-tailed test here, it's just alpha, not alpha over 2. So this is going to give you 2.33 here. Here we're going to have 2.05. Please don't ask me how I got these figures. I'll teach them more tomorrow. But if you may not be there, just memorize these ones with terrible exactness, because these ones need to be known. Okay. And finally, here you're going to have 1.28. Some tables, however, may give you partially these same figures here. At the far end, when you check here, you can see 95%, it has 1.645. At 97.5, it has 1.96. This is, then we have 2.33 at 99%. This is for a single tailed test, which is the right tail. Okay, 99.5%. Although that may confuse you, but at least you may have a chance to know partially. All right, let's get back to our work. So I have taken you through how to identify a single-tailed test and how to identify a double-tailed test. If we want to test a population with a mean less than 50, so this sign is less, so meaning we're shading to the left side. This is a single-tailed test, which will look like this. And if you're given a confidence level of 95%, our Z in that case will be 1.645 because of this table that I've just given you. Please take time to memorize this table. It is your Bible for this course under hypothesis testing. So if you're given 99%, just know that this is 2.58 and that's two-tailed test. Then 2.33, 1.96, and 1.645 for 98, 95, and 90 respectively. 2.33, 2.05, 1.645, and 1.28 for 1, 2, 5, and 10% for a single-tailed test respectively. So now this I must mention to say whenever we are dealing with samples more than 30, we use what we call the Z. Whenever the sample population is less than 30, we use what we call the T. The formulas below are shown. So when our sample standard deviation is known, our Z is equal to X bar minus mu standard deviation over root N. If our population is not known, we can use our sample. We can calculate it. The sample standard deviation ideally is the same thing. And here, if you're using a sample less than 30 and the population mean is known, we use Z X minus mu population standard deviation over root N. If it is not known, we use what we call the T distribution, where we calculate our sample standard deviation here. But ideally, the formula is the same. So for this course, we're going to look at a single sample mainly as the focus for your exam. So just a recap, this denotes a two-tailed test, and a two-tailed test looks like this, where alpha is divided by 2 on both sides. This denotes a single-tailed test on the right whenever you're given our assumption to be tested, showing you a greater assumption. All right, I'll share these notes later on. Then this also shows you a left-tailed test. Then the critical values, you always make a decision to reject or accept HO if our alpha calculated is greater, or our test statistic is greater than the tabulated figure. So these are the decisions that we're going to make. Now, I would want you as much as possible to love this topic because it looks complicated, but it's very, very interesting. The shaded regions here are called the rejection region. Whenever our answer falls within these shaded regions, we are always rejecting our null hypothesis. This unshaded region is called our accept region. Whenever our answer falls within the accept region, both on a two-tailed, on a single-tailed test, we accept or we fail to reject our HO. So whenever we fail to reject or whenever we accept our HO, it means there's no significant difference that exists in the means. Whenever we reject HO, it means there's a difference between the two means that you're comparing. There's what we call a hypothetical mean, and there's what we call a statistical mean. There's what we call a hypothetical mean, and there's what we call a statistical mean. A hypothetical mean is simply a mean that is claimed and is an assumption. This farmer claims that his pumpkins weigh 3.5 kgs. After testing 100 of them, we actually found that they're weighing 3 kgs. The 3.5 is simply his claim. It is denoted by mu. The 3 kg was actually calculated from the 100 pumpkins. Those are actually his um, X bar. So in an exam setup, a question will simply come to say as follows. Suppose a farmer claims that his pumpkins on average will weigh a mean of 3.5 kgs with a standard deviation of 6 kgs. Okay. After sampling a sample size of 36, after sampling a sample size of, let's say, 100 pumpkins, it was found that they actually weighed 3.0 kgs. At 2% level of significance. At 2% level of significance, can we test the farmer's claim? At 2% level of significance, can we test the farmer's claim? So I'm going to be very objective as I'm analyzing this question. Firstly, it doesn't tell us whether the claim says greater or less, it's just silent. So we're going to use a double-tailed test. We're simply going to say number one, we say that the null hypothesis simply states the claim of the what? The farmer. We just say his claim is that this guy, his pumpkins are 2 point or 3.5 kg. So you put mu is equal to 3.5. Then here, so maybe he's lying. It could not be 2.5, but we cannot say they are less than because we're just testing his claim. So we just say these are not equal to 3.5. So this is how you state the hypothesis. In the second step, you state the what? The level of significance. What is our level of significance? Our level of significance has been given as 2%. Whenever you're not given a level of significance, the standard is 5%. So number three, we need to identify our Z. At 2%, our Z is what? Our Z is 98 confidence, meaning the Z is 2.33 here. So this gives you an idea of how the tails will look like. Tails will look like this. On the left side, we're going to have negative 2.33. On the right side, we're going to have positive 2.33. Remember our song, 99, 2.58, 98, 2.33, 95, 1.96, and 90, 1.645. At this stage, I don't expect any of you not to know this. You're writing exams very soon, and this must be at your fingertips, unless you've specialized not to handle this. So this is how it looks like. Then step 4, calculate the test statistic. So since the sample size is 100 greater than 30, we're going to use this formula. Our x minus mu, our population standard deviation is known, so we're going to use this. So our x bar is always attached to a sample size. From 100 pumpkins, they were weighing what? 3 kgs. Then here our mu, the one we're testing, is 3.5. Like I mentioned, hypothesis testing is mainly about testing differences that exist between two means. So we know that clearly the 3 kgs and the 3.5 are different by 0.5. So we want to know the significance of this 0.5. So here we're going to divide the 0.5 over the 0.6 here. What are we getting when you divide these two? Negative 0. What?
0.833.
0.833. Great. So you identify where the 0.833 is. It is inside somewhere here. So whenever it is inside, our rule is to accept. So meaning we are accepting the fact that the difference is negligible. He's saying 3.5 and 3. We can't crucify him so much. As proper statisticians, of course, you may not be penalized for saying accept. All right. We say we fail to reject what? Our HO. Uyumuntu is not really lying. He's not far away from the truth, because 3.5 kg and 3 are more or less the same. So you say we fail to reject HO at what? At level of significance 2%. Since what? Since our Z calculated is on the negatives, it is greater than negative 2.33. If it was a positive, we would have said less. And please be mindful of the negative and the positive signs. It's inside here. Negative numbers are greater on the right. So we're going to reject our HO at significance level 2% and conclude that there is no significant difference between what the farmer is claiming and what is actually on the ground. So at this point, before I proceed, are there any questions? If somebody sent me the tutorial sheet so that I can crack it down. At this point, are there any questions before I proceed? Okay. Now, there's the issue of what we call the p-value. We can also use the p-value in making the decision. The p-value is simply the smallest value of our alpha for which we can reject the null hypothesis. For those of you who will be doing research, usually the p-value is a cardinal element that is used to calculate and make a decision. So this is how we calculate p-value. So calculating of the p-value depends on the authentic hypothesis. So suppose we had our Z calculated, which is x bar minus mu, standard deviation over the square root of n. This is what we call the test statistic. So now this is how we calculate the p-value. The p-value is usually multiplied, if it's a two-tailed test, by 2, the p-value, then the Z statistic should always be greater than, the Z tabulated should always be greater than the absolute value of the Z statistic. What am I saying? If we're going to look at an example where our Z calculated is what? X minus mu The standard deviation over root n is 2.02. Okay, we will need to go and check this figure 2.02 in our table. So our decision must always be to ensure that our p-value should be smaller than the alpha for us to reject HO. If p-value is more than the alpha 0.05, we will fail to reject. So this 2.05, 2.02 will go into the statistical table, check under 2.02. The figure we're getting is 0.9783. 0.9783. This figure here. So we'll subtract this from 1 and we get 0.0217. Now we're going to compare this to our alpha of 0.05. So if this figure is the opposite, if it's greater than 0.05, we're going to fail to reject, we're going to accept our HO. But if it's less than 0.05, we'll reject. So all figures below 0.05, it means it's a significantly different. The means are significantly different. I repeat, if you get your Z value, you need to read it to get a probability, the probability value inside the table. So when you go inside the table, we'll find 0.9783. We subtract it from 1 to get the alpha value or significance value. So we compare this to the alpha. So any figures less than 0.05, we'll say they're significant. We usually reject HO. If the figure is more than 0.05, we fail to reject. It means there's no significant difference. Okay, so we sometimes use a p-value to calculate and make the decision based on that. So many people fail to understand the concept of the p-value. Like I said, the p-value is defined as the smallest value of alpha for which the null hypothesis can be rejected. And the decision is as follows. If the p-value is less than or equal to alpha, we are going to reject. If the p-value is more than the alpha, we are accepting. So in the question that we were just doing here, we could also use the p-value to calculate. So we got negative 0. What? What did we get? 0.883. We pick on the absolute figure itself. So you check for the 0.83 and you're going to compare to the alpha. Our alpha, this is 0.002. If our p-value that we're going to get is 0.83, we'll have to go into the table. Our Z table, 0.083. So 0.08 and under 3. What are we getting? 0.076. 0.07967. So you subtract this from what? From 1. What are you getting when you subtract this from 1? 0.7969. What are you getting when you subtract this from 1? What are we getting?
0.203.
Okay, 0.203.
203.
Okay, so you're going to compare this to our alpha here, this one here, 0.203. Remember, our decision is if this, it's actually opposite that we're doing. If this figure is less than this amount, then we're going to reject. Otherwise, if this figure is more than this, we're going to accept or fail to reject. So the 203 is more. This is like 20% and this 2%. So this amount is more than the 0.02. So the decision is still the same. We're going to do what? To accept. That is how we use the p-value to calculating or making a decision. It is very important. Sometimes the examiner will be specific and will tell you to use the p-value. So the p-value is the smallest value of alpha. We only reject if it's less than the alpha figure. So 1%, your alpha is 0.01, 2%, your alpha is 0.02. And for the p-value, if it's greater than the alpha, we do what? We fail to reject. So we're going to look at an example. I need you to deduce and tell me whether we are going to reject or fail to reject, whether it's a two-tailed test or it's a single-tailed test. So in this question here, a random sample of 10 individuals are drawn from a population of interest that has a mean of 27. Assuming that the population is approximately normally distributed with a variance of 20, can we conclude that the mean is different from 30 years using an alpha of 0.05, and you're told that the p-value is 0.0340. So even though they're doing the calculations here, can you tell me, are we rejecting or we fail to reject in our decision? Our alpha is 0.05 and our p-value is 0.0340. Do we reject or do we fail to reject?
We are rejecting.
We're rejecting. Why are we rejecting?
No, we are not rejecting because our p-value is less than alpha.
No, your first answer is correct.
No, yes, we reject because our p-value is less than alpha. The
Yes.
opposite of this
I
is
agree.
So we reject because our p-value is less than the alpha. Excellent. Additionally, if I may ask, identify for me which one is your mu and which one is your x bar, if there's any. Which ones are mu and which ones are x bar? Which ones are mu and which ones are x bar? Quickly. Our mu has no sample size attached to it. Our x bar has a sample size attached to it. All right. So 30 or 27, which one is our mu and which one is our x bar?
X bar is 27.
27 is our X.
Excellent, yes. Our x bar is 27 because it's attached to a sample size of what? Of 10. We're testing a mu of 30. So our variance is 20. Our alpha is 0.05. So to test the hypothesis, mu is equal to 30, mu is not equal to 30. Then we calculate our z statistic. So our z statistic, our test statistic is what? 2.12. Calculated from our x bar minus mu over standard deviation square root of what? N. So this is 27 minus 30 over standard deviation of what? Our standard deviation was, we're given a variance, we're not given standard deviation. So if you're not given standard deviation, you can use this formula because everything will be square rooted. You can simply say x minus mu over everything under square root, and you can put a variance there over n. because this one is the same as, please don't get confused, these are just mathematical issues. I'm sure those who've done engineering or you're understanding the jargon that's there, right?
Yes.
Yeah, this is the same as this. If you're given the variance per pattern, you can either do the manual way, the grade 5 way, square root the variance becomes standard deviation, and you put it back there, chain. But if you're smart enough to remember, just put it there. 20 minus 30 over our variance of what? 20 over n. Now n is what? N is 10. So you put 10 there, and you square root both of them. The answer you're going to get is negative 2.12. Whether using Z or T at the moment, because the given population sample size is okay. The key thing is the decision rule is this here. We are going to compare this. When you read it inside the table, you go under negative 2 or 2.12. So check under 2.12. 2.12, you're going to get what? 9830. What do you do to the 9830? You subtract it from 1.
You subtract 1.
Then what do you get?
Zero 0.0217.
Good. 0.0217. Then you're comparing this one to what? What is our alpha?
Wow. 0.05.
0.05. Good. So are we rejecting or we fail to reject? We reject because this p-value.
It is less than 0.05.
Yes, we reject. So this is how we make the decision using the p-value under hypothesis testing. This is how we make our decisions using hypothesis testing. So I thought I could stress so much on the p-value because this is coming in your exams. And I needn't sugarcoat it. That this is one of the major topics that goes alongside with what? Estimation. So I'll send you these notes so that you could go through, and I will end this session right now and start another quick session. For those who missed yesterday, I will not take long. I just want to cover up